degradation of pesticides using plastic. Oh my gosh. Complexes. I feel like these titles keep getting longer the longer we go on.
Okay, so this summer, I spent my time working on the degradation of pesticides using plastic molybdenum complexes. More specifically, I was using organophosphates, which are an extremely common type of pesticide used all throughout the world and in the US. So some of you might be wondering, what is an organophosphate? All an organophosphate really is organo means carbon containing, or it's an organic molecule, and phosphate means it contains a phosphorus atom. So all an organophosphate is a phosphorus containing organic molecule. So how do organophosphates work? All organophosphates work by damaging an enzyme called acetylcholinesterase, which is essential in our nerve system. Without this enzyme, we build up acetylcholine, which is a chemical that sends the signals between the nerves. With the excess of this chemical, our nerves become overactive, and we eventually become paralyzed and die. So my summer research has two main applications. The first one is to help prevent health risks in humans. So chronic exposure to these organophosphates has links to lowered cognitive function, psychiatric disorders, ADHD, and memory loss. And with enough acute exposure, it can lead to death, but we are more worried about the chronic, long-term low levels of exposure. So here are 4 of the most common organophosphates used around the US and the world. Glyphosate is the most common by far. It's commonly known as Roundup. It is available for residential use. It's relatively non-toxic compared to the rest of them. In fact, you need 336 grams to kill you. But we aren't really worried about that. We're more worried about the long-term exposure and the long-term effects of it. I've worked mostly with diazenon, which was banned in 2000 for residential use, but it is still available for agricultural use. It's much more toxic than the glyphosate, as only 24 grams are required to kill you. I didn't really work much with chlorpyrifos and parathion, but my coworkers did and all. The second main application for my research is to help complete the phosphorus cycle. So phosphorus is an extremely important resource, but we only have a finite amount of it. Currently, most of our phosphorus comes from phosphorus-containing rocks from countries like Morocco, Algeria, and China. So we need to find new ways to get more phosphorus, as it's used for everything from fertilizers to batteries to preservatives. This issue is actually so important that the NSF, or the National Science Foundation, had a workshop about it in 2015 called Closing the Human Phosphorus Cycle. So now into some methods. This is our plastic molybdenum complex. So as you can see on the left, those are polymer beads. They're sort of an off-white. And then to transform them into the molybdenum complex, we would take molybdenum powder, which is a dark gray substance, and hydrogen peroxide. And when we mix those, it's a highly exothermic and violent reaction. And by the end of it, we get this bright yellow liquid. So we would just dump the beads in there and mix them overnight. And by the end of that night, in the morning, we would have those bright yellow beads on the right there. So this is an energy dispersive X-ray spectroscopy graph that was actually taken by a former ASE student, Joe Seaman. All this is really showing us is that the molybdenum did bind with the beads. And this can also be seen in the scanning electron microscope images. We can see that the molybdenum-coated beads have obvious silver parts to them, that we can see that the molybdenum did bind with it. And the original polymer beads and the depleted beads don't have those. So these beads need an activator. In our case, we used hydrogen peroxide. So when we have just hydrogen peroxide, the pesticide will not degrade. When we have just the beads, the pesticide will not degrade. The only conditions that support the degradation of these pesticides is with both the hydrogen peroxide and the beads. So here is the mechanism for the degradation of diazenon. It is degraded into phosphate, sulfate, and diethylphosphite. Diethylphosphite is an extremely useful substance. as it can be used from anything from a plasticizer to a flame retardant, so it's actually worth quite a bit of money. I mostly focused on the sulfate and the diethyl phosphite. The sulfate we were able to track, so we were able to track the rate of the reaction by tracking these two substances. So we tracked the diethyl phosphite using P31 NMR, and we tracked the sulfate using a barium sulfate assay using the UV spectrometer. So for the P31 NMR, it's a lot like an MRI. All an NMR is a MRI, but on a much smaller scale. So where an MRI has an entire person in the middle of it, that you can get images of the organs, the NMR just has like around a mil of liquid, and then we can just track whether or not there's phosphorus in it. In our case, you can tune it to other substances too. So where the peaks are and how high the peaks are like how much phosphorus there is, and depending on what the phosphorus is attached to, it shifts. So here is an NMR graph. Basically, in our tests, we would take a 1 gram vial, so just a small vial. We would add in the beads, the hydrogen peroxide, the pesticide, and a solvent, in our case, acetonitrile. So basically, we would mix this all together. And this was extremely small amounts. So I was using 5 to 10 microliters of diazinon in this case. So that's 5 to 10 millionths of a liter of diazinon. So there was no danger here. And then we would put it in a heat bath, depending on what temperature we're testing on that day. Then every half an hour to an hour, we take out a sample, put it through the NMR, and put the sample back into the vial. So here, this is at 40 degrees Celsius, and it's a really simple graph to look at because there's only one reactant, which is the diazinon, and there's only one product, which is the diethyl phosphite. So we can obviously see as time progresses, the diazinon is being degraded and the diethyl phosphite is forming. And this is at 40 degrees Celsius, and it took around 2 hours to complete. We also did this at 30 degrees Celsius, which took around 5 hours to complete, and then room temperature around 20 degrees Celsius, which took around like 16 hours to complete. We could have gone lower, but at that point, it literally would have taken all week, and we just didn't have the time for that. So this is a method to, this is the barium sulfate assay. It is named, or I might have been named, by Kelly Mason, who is a senior at Lewis and Clark College where my internship was held. He calls it the IKEA method because it is simple, fast, and it's Swedish. So basically the IKEA method, we just start with the same 1 gram vial of the pesticide, the solvent, the hydrogen peroxide, and the beads. And then every 15 to 20 to 30 minutes, this is a faster, we would take out 200 microliters, then we add in 800 microliters of deionized water, and 1 mil of a conditioning reagent, which is just hydrochloric acid, salt, ethanol, and glycerol. We would mix this all together with some barium chloride, and basically what would happen here is the barium chloride would dissociate, and it becomes barium sulfate. And that barium sulfate we can measure using the UV spectrometer at 420 nanometers. So here on the left, we can qualitatively see it. As more sulfate is formed, the samples become more and more cloudy. And then on the right here, we can see it quantitatively. As these lines are all from different times. So as time progresses, you can see the absorbance is getting higher and higher at that 420 nanometers. So with the data we gathered from the NMR and the UV spectroscopy, we were able to get 2 activation energies by tracking these 2 different atoms with 2 different methods, but this is for the same reaction. So for the NMR, we were able to get an activation energy of 7.88 kilocalories per mole, and then with the UV spectroscopy, we're able to get an activation energy of 8.88 kilocalories per mole. This is actually really good results for us because they are so close to each other. That means that they are reliable for us. So in conclusion, the temperature-dependent kinetics show that our activation barriers with both NMR and UV spectroscopy were very similar. Actually, previous research did this in ethanol instead of acetonitrile, which has the ability to hydrogen bond. So we compared it with that, and the hydrogen bonding in ethanol actually increases the activation barrier compared to acetonitrile. And for future projects, we want to study another organophosphate, probably chloropyrifos, which is one I mentioned at the beginning, which is more toxic than the diazenon I studied. And we want to compare it to diazenon, but this one is actually hard to work with since it is a solid. So trying to weigh out 5 milligrams would be a pain. And for acknowledgements, I'd like to thank the Lewis and Clark Chemistry Department and Professor Lewis Quo, who was my mentor. Past work by Kelly Mason, Madison Ames, Jordan Gonzalez, and Ellie Draves, who are all working with me this summer at Lewis and Clark. Joe Seaman, who is a former ASE intern. Saturday Academy for providing me this experience, and the National Science Foundation. Thank you.
Did your team discuss what the practical application of this would be?
Yeah,
then?
so there's 2 main practical applications. One was the health risks, so if you can degrade these pesticides into safer chemicals, this will hopefully lower the exposure to humans and lower health risks. And also to complete the phosphorus cycle, so we can get another source of phosphorus.
Right, and so would you, what would you do then? Like go to an area where there's contamination and then put the pellets and the activation materials
No,
and
this
so
would
forth?
mostly be like in water treatment.
Water
So,
treatment.
Yeah, from all the runoff
Okay.
pesticides.
Yes.
And also if they're like stockpiles of pesticides, we can degrade all of that
Okay.
into usable
Oh, very
phosphorus.
nice, stockpiles, that's great. Okay, thank you.
Sam, where do you see your career headed with this? This is amazing.
Well, I don't.
Because Roundup's all over the news.
Yeah, Roundup has been everywhere.
Yeah.
And Madison Ames is actually working with Roundup this summer. We were able to degrade it. I'm not sure exactly how successfully, but we were able to degrade it to some degree. So there's definitely potential in this.
So where do you see yourself?
Myself, probably not in the pesticide field. I'm most likely to want to go pre-med than medical, so not necessarily related to this, but I still enjoyed the experience. Thanks.
So you talked a lot about the health risks of these pesticides.
Yeah.
With the materials you degraded it into, how about health risks of those? Did you make it safer?
So all of the products I talked about here, they are safer. They don't have health risks to humans, but it is possible to degrade these pesticides into a different chemical. I don't remember the name. It's like oxone or something along those lines. It's actually 10 times more dangerous than these pesticides. So we try to prevent that.
And then finally, I know you used small amounts.
Yeah.
How else did you and your lab mates use personal protective equipment?
I mean, we always had gloves and goggles, and oftentimes we use the fume hoods. But also these are liquids, so it's relatively easy to keep exposure down. And like I said, it would take 28 grams to kill me, and this is about 5 millionths of a liter. So I don't know what that would be in grams, but very, very small.
Do you know how stable are these organophosphates? Because you mentioned that the diazenon is not really used anymore. Is it still present in water streams?
Well, it is still used, just not in residential use. It's used in agricultural use.
Or it's still used?
Yeah, but it's not used nearly as much as glyphosate. So I'm not sure if any diazenon would be remaining from the residential use 20 years ago, but it might. I'm not
Big
actually sure.
farms
about that.
still use it, right?
Yeah.
So it can be present in water streams?
Yes, it's actually still used here in Oregon.
Okay.
Thank you.